Our last section in this unit is on derivatives of inverse trig functions, and ultimately what this is going to come down to is just the application of some formulas. And they're pretty nasty, most of them, but just so that you see that there's a mathematical basis in them and they're not designed just to make your life miserable, we're going to develop one of them. We're going to develop the inverse sine formula, and then we're just going to use the formulas to find derivatives of inverse trig functions. Before we begin the calculus, let's take a few minutes and review what an inverse trig function is. So basically what you're doing is you're reading the trig chart backwards. And I have brought in a table here for you so we could go through a few examples. So first of all, the notation. Y equals sine inverse of x. So just like we did with the regular inverse function, that little -1 means an inverse function. And another way you'll see it written is this arc sine. So realize that these two are synonymous, that little -1 and then this word arc. And here's the domain and the range of the inverse sine. And you would get a question similar to this. So this is saying the inverse sine of 1/2. And just like when we did regular inverse functions, the question that's really being asked is this. Sine of what equals 1/2? Because remember, inverse functions, your x and your y switch. What I'm really looking for in this trig table is where the sine equals 1/2. And I see that occurs at pi over 6. So my answer to this is pi over 6. So since sine of pi over 6 is 1/2, the inverse sine of 1/2 is pi over 6. Notice it was exactly what we did before when we did inverses. The x becomes the y and the y becomes the x. Inverse cosine is going to work the same way. Here's those two notations. So you're either going to see cosine inverse with the little -1, or you're going to see it called arc cosine, and they're used interchangeably. This says cosine inverse of -square root of 2 over 2. What the question is really asking is cosine of what equals -square root of 2 over 2. And I can see from my table that that square root of 2 over 2 is appearing right here under the cosine column. So cosine of 3 pi over 4 equals -square root of 2 over 2. Therefore, inverse cosine of -square root of 2 over 2 is 3 pi over 4. And our last one is on inverse tangent. Here's our same notation. An inverse tangent of square root of 3 means I'm going to look down the tangent, I'm going to find square root of 3, and my answer is whatever that angle is, which is pi over 3. Now that you're reviewed on inverse trig, let's see how this applies to our calculus. Let's get rid of this little table here. And you see here we have the derivatives of all 6 of these trig functions. The ones that are going to be important to us are just the first 3. These are the ones that are going to appear on the AP exam, and you'll see that reflected in our examples as well as in the Delta Math. Just so that you understand there is a mathematical basis for developing these, we're going to develop this first one for the inverse sine over here. Our first statement here is just how we were thinking about these inverse trig values that we were doing up here. So if we think of inverse sine of x equals y, then that means my x goes here and my y goes here, and I get sine of y equals x. And that's all I've written here. I've just switched things around. And I'm going to do the derivative of x equals sine y. And I start that by doing the derivative of x, which is 1. And the derivative of sine y with respect to x, notice that I have that discrepancy in variables, so I'm going to have to do implicit differentiation here. So again, we're thinking of that y as an inside function, so I do derivative of the outside, which is cosine, leave the inside function alone, which is the y, times derivative of the inside function. And if I'm trying to find dy dx, I'm just going to divide by cosine y. If I want this derivative of y to be in terms of x, I'm going to work a little bit to try to get this to be in terms of x. And I'm going to use that identity sine squared y plus cosine squared y equals 1 to help me get there. This was that Pythagorean identity that we had used before. And since I'm interested in cosine y, I'm going to solve this for cosine y by subtracting that sine squared y first, and then doing the square root of both sides. And that gets me to here, and notice I rewrote this sine squared y as sine y, the quantity squared. And so far this is still in terms of y. But if I look back to where I started, I said that sine of y equals x. So I'm going to make that substitution right here, and in place of that sine y, I'm going to replace it with an x. And then one more substitution to bring this back in place of that cosine y, and I'm pretty much there. And you can see that that derivative that we just came up with matches what our derivative of that inverse sine is here. The difference is this has the chain rule embedded, that's why you have the du dx, but other than that it's the same formula. So let's see how we are going to use this with a few examples here. I think what you're going to find is the actual application of the formulas is not that hard. It's the algebra in the simplification that is a little bit tricky because these are asking us to express in simplest form. Our first question involves an inverse tangent, so my first move is to pull out this formula right here, and I can see that my u is this x over 6. And I see I'm going to have to multiply times the derivative of that u. Let me go ahead and find that derivative, and it might be easier to think of this instead of x over 6, which might make you think of a quotient rule. It's easier to think of this as 1/6 x, and then you can just use a power rule. So my du dx is just going to be 1/6. And now I just apply my formula, and I know my u is this x over 6, so in place of the u, I put the x over 6 plus 1 times du dx, which I know is 1/6, so I go times 1/6. The calculus is over at this moment. It's the simplifying that I'm going to do from here on out. I'm going to start by squaring out this x over 6 first. And when you square a fraction, you square the numerator and you square the denominator. And knowing that I'm going to have to add these, I rewrote that 1 as 36 over 36, so I set myself up with a common denominator. And then I went ahead and added in that denominator, so x squared plus 36 over that common denominator in the denominator of 36. I'm going to take care of this complex fraction. 1 divided by x squared plus 36 over 36. All I do is multiply by the reciprocal of this thing. So this simplified to 36 over x squared plus 36. And now I see that I can divide out a 6 here. So that becomes a 6 and that becomes a 1. And this will give me my final answer. And this is my final simplified answer. And as you see, the actual calculus involved was pretty simple. It was all the algebra that happened after I applied that original formula that got a little tricky. Let's take a look at example number 2. This one will be a little bit simpler for us. So I see this is an arcsine problem, and I see that my x squared is the u in the formula. And I know the derivative of x squared is this 2x. And from there, I'm just going to apply my inverse sine derivative formula, which is right here. In place of my u, I put my x squared. And in place of my du dx, I put my 2x. And now I'm just going to square this out. So I'm going to multiply these exponents and write 2x in the numerator. And once I do that, there's not much else I can do with that answer. Just a word of caution. Don't look at that denominator and think that that's 1 minus x squared. We can't square root each one of these terms individually like that, so don't try to simplify too much. It's good exactly where it is right here. Example 3 is going to have us apply the formula and then evaluate at a specific point. So I'm going to start by using the inverse cosine formula. I'm first going to find my f prime of x, and then I'm going to plug in a square root of 3 over 2. So my inverse cosine formula is this one. And my u is just simply that x. And just following that chain rule that's happening at the end, this times 1 is just the derivative of x. Whether you write it or not, it doesn't matter. A common mistake is to forget to do that chain rule, even though it doesn't really have an impact on this problem. And now that I have my f prime of x, I'm going to find f prime of square root of 3 over 2 by plugging the square root of 3 over 2 into this formula. And now I'm just going to square this fraction. So I square the numerator and the denominator separately. And that gets me to here. I then go ahead and do the subtraction. So 1 minus 3/4 is 1/4. And I can go ahead and square root the numerator and denominator separately. That'll take me to 1/2. And dividing by 1/2 is the same as multiplying by 2. And I get my final answer of -2. And again, realize the calculus was over at this moment right here. If this didn't have the direction to express in simplest form, I would have stopped at this moment. But because it told me to simplify, I had to do all of this algebra and get my answer to be -2. Our final example is going to take us back to our very first derivative lesson, which was that formal definition of a derivative. So you should recognize the similarities. And here is that limit definition. And you can see that my f of x is sitting right over here. And this is my f of x plus h. The only difference is I actually have a value plugged in for the x. I have the square root of 29 over 5 in place of that x. So what I'm going to have to do is recognize this arctan as my f of x with the square root of 29 over 5 plugged into it. So my f of x is arctan of x. And this limit is finding that derivative, f prime, with a square root of 29 over 5 plugged in, so f prime of square root of 29 over 5. So let me start by finding f prime of x using that inverse tangent formula. My u in the formula is simply just that x. So I place the u with the x, and this is the derivative of x, which is just times 1, which is unnecessary to write, but just so you see that chain rule going on. And what this limit is actually wanting me to find is f prime of square root of 29 over 5. So now I've got to plug in that square root of 29 over 5 for my x. And this would be a fine answer except for this part of the directions that say expressed in simplest form. So I'm going to have to algebraically simplify this a little bit. So I'm going to go ahead and square out that fraction. And anticipating my next step, I went ahead and rewrote that 1 as a 25 over 25. Now I'm going to go ahead and add the fractions in that denominator. And then handle this complex fraction by multiplying by the reciprocal, and this becomes 25 over 54, and that is my simplified answer. And again, using these formulas isn't really that bad. It's the simplification part that gets a little challenging sometimes. If you're not asked to simplify, then don't. And also don't forget the chain rule that goes on if you have something more complicated than an x, like what happened on this one up here. You have to remember that you have to multiply by its derivative, this du dx part.